This video will focus on how to calculate formal charge and then how to use formal charge in order to figure out what Lewis dot structure is most likely. So again, one of the pitfalls of Lewis dot structures is the fact that you can draw a lot of things that don't actually happen in real life. Formal charge is one way to help us calculate based on kind of electron strain and proton existence, what structure is most likely. So as we have isomers and resonance structures, and we can draw lots of possibilities, how do I know what's true? Formal charge is based around the idea that when we covalently bond something, we don't lose any electrons or protons, so the overall structure ends up being neutral. Something that happens then is if you transfer too many electrons away or give too many electrons towards an atom, you can have an unequal balance between protons and electrons that life just wouldn't allow you to do. So formal charge allows you to look at how many electrons it originally had before it bonded, how many it had after you bonded them, and kind of what strain or charge you're influencing on the atom because of your movement of electrons. Okay. The one thing about formal charge then is overall, as you figure out the formal charges, they have to add up to be whatever the charge in the atom is. So formal charge is something we calculate for every single element within our structure, and I'll kind of walk through an example of what formal charge allows you to see. We're going to use carbon dioxide as our example because it's one we did right away at the beginning, but it is one that looks like it could resonate or have different isomers if you didn't know some of the original rules. So using the math method from the very beginning of Lewis dots, we find that carbon dioxide ends up having 4 bonds and 4 lone pairs. Given the structure of carbon dioxide, though, I could draw different isomers of carbon dioxide. Okay, I could potentially say I think it looks like this, with an oxygen in the middle. Now that breaks our least electronegative element in the middle rule, but hey, it could happen. Or I think it's like this, where it flowers from the center. Now, of those structures, there's also multiple ways I could put out the bonds. For this structure, I could put them out with a double bond on each side, which is what we ended up doing. But I could also go 3 and 1, and that still satisfies the 4 bonds. So I could do the same thing here. I could go, 2 double bonds, or I could go a triple and a single, or a triple over here and a single. So there's lots of different isomers, which these are isomers, or resonance structures within carbon dioxide. Now for each of these, I also need 4 pairs of electrons, and those would just go out wherever I need to in order to get myself to octets. So for formal charge, for every single atom that's being bonded, I would do a calculation on what the formal charge would be for that atom. So for every single atom that is bonded, I would count up how many valence electrons it had before I bonded it, and I would subtract away, now that it is bonded, how many unshared electrons, pairs, how many total unshared electrons it has, and then how many bonds it has. So for carbon right here, it came with 4 valence electrons. Now it has 4 unshared electrons and 2 bonds, which ends up giving me a total of a -2 formal charge on that carbon. This oxygen came with 6. Now it has 4 bonds and no lone pairs, so that has a +2. And now this oxygen came with 6. Now it has 4 and 2, which means it has a 0. So those are the formal charges on each atom. You can see that -2 + 2 + 0 is 0, which is good because this molecule right here has no overall charge. Okay. So we could just continue to calculate that for every single isomer and resonance structure I have. So like this carbon came with 4. Then I would subtract away 3 bonds and 2 lone pairs, so I would have a -1. This came with 6 minus the 4, so it has a 2. This came with 6 minus the 6 dots minus the 1 bond for -1. And again, they all add up to 0, which is what I would need. Down here, this oxygen came with 6. Now it has 4 dots and 2 bonds, so that has a 0. This carbon came with 4. Now it has 4 bonds and no dots, so that's a 0. And then this oxygen is the same as this oxygen, so he's a 0. Down here, this one had 6. Now it has 6 dots and 1 bond, so that's a -1. This carbon was 4. It has 4 bonds and no dots, so that's a 0. And then this oxygen came with 6. Now it has 3 and 2, so it has a +1. So all of those are just how to calculate formal charge. How do I get these numbers? What this is saying then is how many protons and electrons it had to begin with when it was neutral. Now that you've bonded it, you've kind of created an unequal distribution of the electrons to the protons, right? So this carbon only had the equivalent of 4 protons to 4 electrons in its nucleus, and now you have a surplus of 2 electrons on it. Not necessarily a bad thing, it's just information. Okay, so these are formal charges. You're essentially creating an unequal distribution of electron to proton on each atom based on how you're sharing electrons. The optimal formal charges are the ones where the structure ends up being closest to 0 because you haven't added any undue strain onto the atom. Or if you can't make a resonance structure or an isomer where all of the formal charges on each atom is 0, then the next best thing is to have a negative formal charge on the atom that's most electronegative. So if I was dealing with carbon dioxide, a structure where my negative ends up on my oxygen, I would be like, okay, that's not bad because oxygen's the most electronegative. So I know for sure that this is wrong because my oxygen ended up being positive and my carbon ended up being negative. And that's just not going to happen. In real life, my most electronegative one is going to be drawing electrons toward itself. It's going to end up being the -1 for sure. And so then same here. This is no good. Plus, as you look, this structure we ended up drawing right here, they all ended up being 0, which is why that ends up being the most likely and most abundant structure for carbon dioxide. You have your least strain on your charges right here. This guy is not bad. I only have -1s, not 2s, but the -1 and the +1, both being on oxygen, potentially we are resonating into the structure, but it's not the most likely. So formal charge helps you identify which resonance structure and isomer is most likely if you're not sure. This is one example. We'll do more examples in class, so don't panic, but this is just a reinforcement of how the math works. That's it. Have a nice night.